Hi everybody, Mrs. Pesic here. We are looking at section 6.7, Modeling Real-World Data. Your objectives are to apply functions to problem situations and use mathematical models to make predictions. Much of the data that you encounter in the real world may form a pattern, and many times the pattern of the data can be modeled by one of the functions that you have already studied in this course. You can then use the functions to analyze trends and make predictions. So let's recall some of the parent functions that you've studied so far this year. So we have studied, let's start with this. We have studied linear functions. So linear functions would be like f of x equaling x. The graph looks something like this. And then when we look at the data though, there's going to be constant first differences between y values whenever we have evenly spaced x values. So you'll always look at a table of values and it'll have evenly spaced x values, and then when you take the first order differences of the y's, they're always equal. So it's a linear function. Then we have quadratic functions like f of x equaling x squared. And then if we have evenly spaced x values again, then we check the first order differences. They won't be equal, but the second order differences will be equal. All right, and then let's take a look at exponential functions. Exponential functions would be b, like f of x equaling b raised to the x, where b is going to be greater than 0. And so in this case, there will be constant ratios instead of constant differences. There's going to be constant ratios between y values. Again, evenly spaced x values. So all of these first three have evenly spaced x values. All right, but the one that's a little different is this last one. That's the square root. So f of x equaling square root of x. We haven't done too much with square roots this year, but you know that the graph looks something like this. And those have constant second differences, just like the quadratics did, but it's constant second differences between the x values for evenly spaced y values. So that's the one that's going to be different. That's got evenly spaced y values instead of x values. All right, so here's a helpful hint. Because the square root function is the inverse of the quadratic function, the constant differences for x and y values are just switched. So again, constant second differences for y's, when the x's are evenly spaced, that's a quadratic. But if it's constant second differences for the x's, when the y's are evenly spaced, that's square roots. All right, let's take a look at our first example. Identifying models by using constant differences or constant ratios. So use constant differences or ratios to determine which parent function would best model the given data set. Okay, so on this one, we have time goes up 5, 10, 15, 20, 25, and the height in inches. And what I want you to notice is that if we're looking, let's consider the time as like the x and the height as the y. Our x's are evenly spaced. I go up by 5, go up by 5, go up by 5, go up by 5. So these are evenly spaced x values, which means we're going to look at the constant differences for the x's. So for the y's. So let's see what's the first order difference. We want to subtract 198 minus 163. And I'm just going to pull up my calculator, and I'm just going to do this on Scratchpad real fast. I'm just going to do 198 minus 183. Was that right? Let's see what it was. 163, excuse me. That gives me 35. All right, so I know that that's 35 here. And let's try another one here. How about 163 minus 128? So if I do 163 minus 128, that's also 35. And if we test this, all of these constant differences turn out to be 35. So for all of them, if that first order difference, they're all equal, they're all 35, so that makes this a linear function. All right? So since this is linear, these are the steps that we're going to be following. We're going to determine the best model to fit the data. We just did that. It's linear because the first order differences for the y's were all equal when the x's were evenly spaced. Then the next thing is we're going to enter the data on a list and spreadsheet page and then go from there. So at this point, now's the time for you to start a new document on your calculator. So go to your calculator. I'm in Scratchpad. I'm just going to push escape from my Scratchpad, and I want a new document. All right, and actually, you're actually not going to make a new document. You're going to do all of this in the document that was sent to you in class. You were sent a blank document. So go ahead and open up that blank document, and we're going to enter a list and spreadsheet page. All right, so here on your list and spreadsheet page, you're going to click, let's call this X here, and we're going to call this Y here, and we're going to enter our data. So where is that data? So that data, let's pull this up from here. It was 5, 10, 15, 20, 25 here. 5, 10, 15, 20, 25. That was our X's. And then when I go back to my Y's, I'm going to enter 58, 93. And then it went 128, 163. And lastly, it was 198. All right, so all that data has been entered, and so that was, that's the first step. So if I go back to my directions, let's kind of check these off. We just did this one, determine the best model. We said it was going to be linear, and now we've just done this one. We entered the data on a list and spreadsheet page. So now let's actually look at the data on a data and statistics page. So this is on your document. We're going to add a new page, so Control Doc. To add a page, and we want a data and statistics page. And again, here you're going to go down here to the bottom. You're going to click. It says, oh, what variable do you want on the x-axis or the horizontal axis? We want the variable that we called x. And I'm going to click over here and make this y. There's our data, and it sure looks linear. So let's kind of check off that we did that. We plotted the data. All right. And then the next thing is we're going to go to a calculator page to do the appropriate regression. So back to our document. On our document, I'm going to add a calculator page, and I want to do regression. So I'm going to go to menu, and I want statistics, and I want stat calculations, and I want linear regression. There's really two for you to choose from. Let's just go with the first one. And it says, oh, what's your X list? Well, we just called it X, and I'm going to do a little drop down here for my Y, and then I get Y, and then I'm going to say okay. All right, so it's telling me that this data can be modeled by Y equals mx plus b, where m is 7 and b is 23. So let's write that down, that that we just did this, okay, and our model is going to be Y equals 7x plus, let's see, what was it again? It was 7x plus 23. So that's our model, best fitting model for this. All right, now we're going to go to a graphs page and pull up a graph of the model to help answer any follow-up. And hey, I've got a follow-up question for us. So let's go to a graphs page. You're doing all this on the document to show your teachers. And then here I'm going to go to a graphs page, and it's saying, oh, do you want to enter f2 of x? And no, I do not. I want to do an up click. There's my function, and I'm just going to push enter, and it's graphed for us. All right, let's see what that follow-up question was. It says, use your model to predict the height after 32 years. So I can go back to my graph. I could pull up a table, Control T, and go down to 32. That's one way to go. Or let's look at a different way. I'm going to get rid of my table, Control T. I could actually just go menu, and I could go to trace and graph trace, and I could just type in 32, and it'll take me right to that point. So the answer is 247 for this. So the model predict the height after 32 years, and that turned out to be 247. Okay, and in this case, I think the height was in inches, so 247 inches. Okay, So let's take a look at, oh, and I can say, yes, we did all of this. So we did everything on our to-do list here. Let's take a look at another example. All right, for this one, it says identifying models by using constant differences or ratios. And so in this case, here's the data. Time 1, 2, 3, 4, 5, and the height 132, 165, 154, 99, and so on. So I see that the x's are evenly spaced. They're just going up by 1 every time. So the x's are evenly spaced. So now I'm going to try the first order differences here, and so on. So when I try those first order differences, let's just get right to the answer here. If I want to find those first order differences, okay, those turn out to be negative 99, negative 55, negative 11, 33, depending on which way you were subtracting. If we do right minus left, that's what you'll get. Those are not equal. So the first order differences are not equal, so we know it's not linear. All right, not linear. All right, but if we try the second order differences, then those are equal, because negative 99 minus a negative 55 is going to be a negative 44. Negative 55 minus negative 11 is negative 44, and so on. You could test all these if you'd like on Scratchpad. All right, so now we know that the second order differences are equal, right? They're all equal to each other, so that makes this a quadratic. Quadratic. I'm having trouble writing on this. Okay, so if it's a quadratic function, we're going to do all the same steps that we just did, and then we do have a follow-up question here. All right, so we already did part A. We determined the best model for this data. So let's go ahead and enter this data. But here's the thing. If we just say, oh, let's add a new page, listen spreadsheet, and I say, okay, I want to enter my x's. Notice that, look at that, that x is big and bold, and I push enter, and it's already going to fill in all the x's, but these are not the x's we want. These are the x's from the previous problem. So that's an issue that we need to solve right now. So in other words, see how it's 1.3, 1.4, 1.5? That means you're on problem 1, page 5. This was problem 1, page 4. So we don't have the same x's from the previous problem, so we're able to enter new x's. Here's what we're going to do. Everybody do this with me. We're going to do Control and up click. That's going to take us to the page sorter view, and notice all these are in problem 1. But we want to start a new problem so we don't have that issue with the x's. So go to Menu, and it says Insert Problem. And say, oh, you want to enter problem 2? We do. So we click here, and Menu. Now I can go to a Listen Spreadsheet page, and I can say X, and it's not big and bold, and it's going to let me enter, whoops, and it's going to let me enter the x's that I want for this problem, which were just 1, 2, 3, 4, and 5. All right, so we got those entered, and I'm going to put a y up here, and the data here, starting right here, is 132, 165, and then it goes 154, 99, 0. All right, so there's my data. By the way, make sure you push enter after that last one, right? Don't leave it hanging here and over the 0. Got to push enter. All right, so we entered the data on a Listen Spreadsheet page. That was like step B. Now we're on to step C. Let's just take a look at this data on a Data and Statistics page. Again, notice we're on problem 2, page 1. So let's add a new page to this problem 2, and this is going to be a Data and Statistics page. I'm clicking down here, and there's my x's all lined up. Remember, they're evenly spaced as they're supposed to be. And I click over here for my y's, and I'm getting a graph that looks like that. Yeah, that looks like it could be a quadratic. Let's see what the model is going to be for this. So now we're on to a calculator page to do the appropriate regression. So we're going to do Control, Doc, and we're going to a calculator page. And remember, our steps are Menu, Statistics, Stat Calculations, and this time we want option 6, Quadratic Regression. So here I'm going to do a right click, and I'm going to choose X for the X list. I'm choosing Y for the Y list, and I'm going to say OK. And there's my best fitting model. So I get AX squared plus BX plus C. My A is negative 22, B is 99, C is 55. So this is going to be y equals, and this was negative 22x squared, and then plus 99x plus 55. All right, so that's my answer for the part D. And then we're going to go to a graphs page, pull up a graph of the model, and say, well, what's the height going to be after 2.7 seconds? So I am going back here. I'm going to add a graphs page, Control Doc, graphs page. And it's saying, oh, do you want to enter something for F2? No, I want my F1 because it's already stored there. And I can push enter. And again, remember our trick, we said menu, and we said trace, and we said graph trace. And I think we were putting in, what, 2.7 seconds. So I'm just going to do 2.7. It's going to take me right to that point. And it looks like it's going to be 162. So the height after 2.7 seconds is 162. All right. Okay, so that's that problem. Let's take a look at another example. In this one, it says identify models. We're still looking for constant differences, but if we don't find any, we're going to try constant ratios. So in this, we've got time versus population. Again, are the x's, again, this is going to be like our x's. This is going to be our y. Are the x's evenly spaced? Well, sure, 4 to 8 is 4, 8 to 12 is 4, 12 to 16 is 4, 16 to 12. So these are all evenly spaced. So then we're going to try doing the first order differences and see if this data is linear. If it's not linear, then we'll try the second order differences and see if they are quadratic. All right, you can do that subtraction on your calculator like on a scratch pad. Let's just call up and see what actually happens here. The first order differences, definitely not equal. That's no good. And if we try the second order differences, they are also not equal because I get a 16, a 15, a 15, not equal. So what we're going to say is it's not linear, it's not quadratic. So since neither the first nor the second differences are constant, let's check the ratios between the consecutive y values. Ratios instead of differences, right? So ratios, in order to do that, we need to take not 8,493 minus 8,847, but we want 8,493 divided by 8,847. So if we do that, we end up getting, let's see, I think that I have it this way. So I've got 9,600 over 10,000. That turns out to be 0.96. 9,216 divided by 9,600 turns out to be 0.96. This one's also very close to 0.96. This one's also very close to 0.96. So because the constant ratios are all very close to 0.96, we can conclude that it's an exponential model. All right, that will best fit the data. All right, well, now that we've decided, hey, looks like exponential data, then we can do the same 5 steps that we've been doing. All right, and so let's go ahead and we've already done part A. We said, hey, it's not linear, it's not quadratic, and we tried dividing instead of taking differences, and we got it to be constant ratios, so that made it exponential. So let's go ahead and enter this data on a listen spreadsheet page. Again, though, remember what's our trick here? We don't want to be in problem 2 anymore because we're going to enter new x's and new y's. So let's go to Control up click. And remember that lets us enter a new or start a new problem, not just a new page. So I'm going to go menu and insert problem. And it says, oh, you want to start with problem 3? Yes, I do. Thank you. And so here I press menu. I'm going to go to list and spreadsheet. And here I'm going to enter an X. And I'm going to enter the data that I have here, which was 4, 8, 12, 16, 20. Okay. And then I'm going to go over to my Y column, and the data here I want is 10,000, 9,600. And then I want 9,216. And then I need 8,847. And my last one here is 8,493. All right, remember, you got to push enter after that last entry of the data. So at that point, we're going to add a data and statistics page so we can see this data. So data and statistics page, and I'm going to click, and I'm choosing, I see a problem. Let's go back a page. Let's see, let's say escape. Control left click. I see the problem. I forgot to call this Y. We're learning what not to do. So we're going to call that Y so that when we go back to our data and statistics page, let me just start a new one, data and statistics. I can click here and say X, and I can look at those evenly spaced, right? X values. And here I'm going to say Y. And then there's my data. It kind of looks linear, but I think the idea is it's gently being an exponential decay function. So at this point, if we're following along on our steps, what have we done so far? We entered the data on a listen spreadsheet page. We plotted the data on a data and statistics. Let's go to a calculator page now and do the appropriate regression. So I'm going to a calculator page, Control Doc. Calculator page. Notice I'm on problem 3, page 3. Previous one was problem 3, page 2, and so on. I go menu, statistics, stat calculations, and we had decided that this was exponential. So we're going to do exponential regression. I do a right click and I choose X, and I do a right click here for Y list and I choose Y. I say OK. There's my exponential model right there, and it turns out to be, looks like A is 10,416.9. So Y equals 10,416.9, and this whole thing is going to get multiplied by something raised to the X. What is that B value here? Let's see. That B value is 0.9898. 0.9898, something like that. All right, and that's supposed to be a 9. That looks kind of like a 4. All right, so that's our model. That is the model that we want. And so here, I'm now going to enter a graphs page so I can answer a follow-up question. I'm not interested in F2. I'm going to do an up click. There's that model, and I'm going to push enter so it graphs it. I'm not able to see it because I really, if I wanted to see the graph, which I kind of do, I want to go from 4 to 20 on the x-axis, and I got to get up to at least 10,000. Yeah, something like that. So if I go back here, I can change my viewing window, menu, window zoom, window settings. Let's just say 0 to 20. It was 4 to 20, but I'll say 0 to 20. And then my Y minimum, let's just go from, I'll say 5,000 to 10,000. All right, let's see if we can see the graph. There it is. It's a little bit of our exponential decay graph there. All right, what was our follow-up question here? Predict the population after 29 years. So again, I can pull up a table, Control T, and I can go down until I see 29 years. That's certainly an option. There it is. Looks like 7,747 approximately. Or I can, let's Control T, get rid of that table. I can go menu, trace, graph trace, and just type in, what was the number of years? 29 years. I can just type in 29. And there it is, 7.75 E3. Well, E3 means I got to move that decimal spot over. Whoopsie. Let's see. There's my graph. It was menu, trace, graph trace, and it was 29. There it is, 7.75 E3. So if you do see that, 7.75 E3 means times 10 to the third. So in that case, I just need to slide this decimal place 4 spots. 1, 2, 3, 4 spots. Oh, not 4. Why 4? I want 3 spots. Let me try this again. Almost there. So 3 spots. 1, 2, 3 spots. So I just need to fill in a 0 here. So it's really 7,750 approximately for the population in 29 years. All right. Okay, so that's the answer for that one. We've got one last example. Determine the best fitting model for this data below. So, okay, I'm looking at my x's. Are they evenly spaced? Well, from 1 to 4 is 3. 4 to 9 is 5. Those are not evenly spaced. 9 to 16 is 7. That's no good. So what we're going to do instead of that, since they're not evenly spaced, let me get rid of this. Okay, let's check and see if the y's are evenly spaced. From 3.5 to 7 would be a jump of 3.5. From 7 to 10.5 is a jump of 3.5. From 10.5 to 14 is also a jump of 3.5. And so from 14 to 17.5, also 3.5. So this is constant. This is evenly spaced y values. The y's are evenly spaced. All right, so that means it's not linear. We're not going to be looking for linear, quadratic, or exponential. We're going to be testing to see if it is a square root, possibly. Square root question mark. Well, how do we find out if it's square root? Well, in that case, we have to look at the first order differences and then the second order differences for the x's. So let's do it this way. We want to do 25 minus 16. That's equal to 9. And then 16 minus 9, that's equal to 7. 9 minus 4 is equal to 5. 4 minus 1 is equal to 3. Well, the first order differences for the x's are not equal. But if I try and do the second order differences, 9 minus 7 is 2. 7 minus 5 is 2. 5 minus 3 is 2. So since the second order differences are equal for the x's, that means it is going to be square root. All right. So that's great. We found out what the best fitting model is. The best fitting model is square root. And now let's enter the data on the list and spreadsheet page. So again, we're continuing with this document that we have. And so in this case, again, I don't want to put it in problem 3, I need to start a problem 4. I'm going to do Control and the up click, and I'm going to say Menu, Insert Problem. So it says, oh, you want to start a problem 4? Yes, I do. And on the menu, I want a list and spreadsheet page. Now I can type X here and Y here. And now when I'm entering the data is 1, 4, 9, 16, 25 for the x's. Okay, and then my y's are 3.5, 7, 10.5, and then it went 14, 17.5. All right, so I entered all the data, and I'm going to now go to a data and statistics page so I can see this data. I click down here and I say I want the x's here. Notice the x's are not evenly spaced. It's the first time the x's have not been. And I'm going to click over here and choose the y's. And then sure enough, it looks like it's a square root graph. It's got that square root kind of shape to it. So let's find the best fitting model for this by entering a calculator page. And I'm going to go Menu, Statistics, Stat Calculations. Now here's the little tricky part. There's not going to be anything that says square root. There's nothing here that says square root, but there is something here that is going to help us, and that's called power regression. All right, so I'm going to click on that power regression, and if I do X list and choose X, and Y list and choose Y and say OK, there's my model for power regression. It's going to be Y equals A times X to the B, where the A is 3.5 in this case, and the B is 0.5. So I get 3.5 times 0.5 I'm sorry, 3.5 times x raised to the 0.5. So I'm going to write that down here. My model was y equals 3.5 times x to the 0.5. Well, if you remember from our work here, if you have a fractional exponent like that, because this is really 3.5 times x to the 1/2 power, that 1/2 exponent is the same as a square root. So our model is really y equals 3.5 times square root of x. And so that's going to be our model for this problem. And so now we're going to use the model to predict the y value when x is equal to 39. So the best way to do that is to add a graphs page. And I'm going to do an up click so I can see our model. There it is. And I push enter. Sure enough, there's our nice square root looking graph here. And so I am trying to answer a follow-up question, which is find the y value when x is equal to 39. So if I do that, I can just go menu and trace and graph trace and just type in 39. And it takes me right to that point, and it looks like it's about 21.9. So my answer here is 21.9. All right, so hopefully you have a beautiful document with all of your notes from section 6.7. And that's it for this video. Thanks for watching.